Hey everyone, and welcome to this explainer, where we're unpacking some incredible source material designed to be your absolute ultimate chemistry masterclass. Now, if you are tired of opening your chemistry book and just feeling your brain flatline from way too many equations, all those complicated formulas, and what feels like an endless sea of rote memorization, well, you're definitely in the right place. Today, we're breaking that illusion. We are going to completely hack your chemistry exam preparation. We're going to take what feels like a brutal memory test and turn it into a highly predictable, logical system. Get ready, because you're about to dominate your chemistry papers.
Here is our quick roadmap for today. We're going to cover 1. Hacking your chemistry revision, 2. Defining the building blocks, 3. Separating chemical mixtures, and finally, 4. Essential chemistry calculations. All right, Section 1. Hack your chemistry revision. Let's dive right into this. The source material suggests a total mindset shift right out of the gate. You know that feeling when you're just staring at a textbook, hoping facts will magically absorb into your brain? We have to stop doing that. Passive reading is a trap. There's a brilliant quote from our sources that says, "Chemistry is not about memorizing, it's about patterns." And that perfectly captures the neuroscience-backed approach we need to take here. Think about it. Physical chemistry is math-based, organic chemistry is structure-based, inorganic chemistry is trend-based. It's essentially a giant logic puzzle. And once you actually see those patterns, you can completely stop forcing your brain to remember random facts and start predicting how elements will react.
So how do we actually put that into practice? Enter the laser-focused strategy. This is a highly effective 4-step habit stacking loop. First up, you watch a quick 10-minute overview of the topic. Second, you close the book, literally close it, and summarize the concept in your own words on a blank piece of paper. Third, and honestly this is the absolute crucial step, you immediately solve 2 to 3 exam questions related to that exact concept. And fourth, you speak the concept aloud, almost like you're teaching it to someone else. Doing this tight 25-minute loop drastically increases how fast you retain information. It's not magic, it's just really good memory science.
Moving right along to Section 2, defining the building blocks. Grasping these foundational blocks isn't just a nice to have. The sources are super clear that locking down this exact terminology is exactly what the exam boards demand if you want full marks. Let's start with the atom. Most of an atom is actually just empty space, with a tiny, incredibly dense nucleus sitting in the center, surrounded by these orbiting shells of electrons. Inside that nucleus, we've got protons and neutrons. Now here's a super simple memory hack for the charges. Proton and positive both start with the letter P, right? Neutron and neutral start with the same letters too. That just leaves those tiny orbiting electrons as your negative charges. And because the number of positive protons and negative electrons is perfectly equal, the atom as a whole is totally neutral.
But what happens when that balance shifts? Well, you get an ion. When an atom gains or loses those negative electrons, the charges just don't balance out anymore. Now, metals, which you'll find typically on the left side of the periodic table, always donate or lose electrons when they bond, which forms positive ions. Nonmetals, over on the right side, gladly accept those electrons, forming negative ions. It's kind of like a perfect match.
Next up, we have molecules. This is simply a group of 2 or more atoms held together by chemical bonds. And it's really important to note that a molecule can be made of the exact same element, like the oxygen we're breathing right now, which exists as pairs of atoms bonded together, known as O2. Or it can be made of totally different elements, like H2O, which is just one oxygen atom bonded to 2 hydrogen atoms.
Okay, pay close attention here, because this next concept is a classic 2-mark exam trap. You absolutely must know the precise difference between a compound and a mixture. A compound contains 2 or more different elements that are chemically bonded together in fixed proportions. Think of pure water. A mixture, on the flip side, consists of different substances just sitting together in the same place. They are completely physically mixed, but they are not chemically joined. Salt water is a great example of a mixture. The salt is just physically dissolved into the water, but it hasn't bonded with it.
Which brings us to Section 3, separating chemical mixtures.
Now, what's really interesting about this is that because the substances in a mixture aren't chemically glued together, we can use simple physical methods to just pull them apart. And remember, no new substances are ever made here. The source material outlines 3 key methods, and the one you choose depends entirely on solubility. If you have an insoluble solid, like say sand and water, it obviously doesn't dissolve, so you just use filtration. The water passes through the tiny holes in the filter paper and the sand gets left behind. Easy. But if the solid is soluble, meaning it has completely dissolved to form a clear solution, like salt and water, filtration is totally useless. Instead, you have to choose between evaporation and crystallization. So how do you actually choose between the two? This right here is where students constantly lose marks. Evaporation is super fast and easy. You just blast the solution with a Bunsen burner until the liquid is gone. But beware of the thermal decomposition trap. Some solids will actually break down and decompose when they're exposed to that much heat. So if your exam question mentions a delicate solid that breaks down when heated, you must use crystallization. That means using gentle heating, like a water bath, stopping as soon as crystals start to form and then letting it cool down safely.
All right, home stretch. Section 4, Essential Chemistry Calculations.
I know physical chemistry calculations can cause a ton of anxiety, but the sources reassure us that Paper 1 and Paper 2 calculations are literally nothing more than simple, repeatable mathematical steps. Let's tackle the elephant in the room first, Avogadro's constant. Just like the word dozen means 12, a mole simply means 6.02 times 10 to the 23rd power of atoms or molecules. Yes, it is a massively intimidating number. So here is a totally bizarre but highly effective memory hack to lock this into your brain forever. 6 Avengers eating 22 tacos at 10:23 p.m. 6.022 times 10 to the 23. Is it silly? Absolutely. But will you ever forget it in an exam? Not a chance.
When it comes to the formulas themselves, please do not just try to force them into your brain by staring at the page. Use the 3P system instead. First, pattern. Understand the logic by actually deriving the formula once yourself. Second, practice. Immediately solve 3 or more problems using it. And third, placement. Connect it to a visual anchor or a silly mnemonic, kind of like our Avengers eating tacos.
So the crucial point is how we actually use the mole in an exam scenario. Let me introduce you to your foolproof calculation pipeline. Often, a question will give you the mass of one reactant and ask for the mass of a product. You cannot convert mass directly to mass. You absolutely have to use moles as the middleman. The pipeline always flows like this. First, turn your known mass into moles. Second, use the big numbers in the balanced chemical equation to find the ratio of moles from the first substance to the second substance. And finally, turn those new moles back into your final mass. Mass to moles, moles to moles, moles to mass. If you follow that exact pipeline, you'll nail the answer every single time.
Let's quickly run through the high-yield formulas you're actually going to need to run that pipeline. First, moles equal mass divided by relative formula mass. Then we have 2 formulas that get confused all the time: percentage yield and atom economy. Percentage yield is all about reality. It's how much product you actually managed to make compared to the theoretical maximum you could have made perfectly. Atom economy, on the other hand, is about efficiency. It tells you the percentage of the mass of all your reactants that actually ended up as your desired, useful product, rather than just becoming waste.
And brilliantly, that brings us to the end of this explainer. We've looked at how to stack your study habits, define those core building blocks flawlessly, navigate tricky separation methods, and completely conquer the calculation pipeline. You see, you aren't just memorizing anymore. You're actually understanding the underlying patterns. With this framework in your back pocket, you are more than ready to dominate your next mock test. But it also begs a slightly bigger question. If the complex, chaotic interactions of the universe can be simplified into these predictable, highly hackable patterns on a piece of paper, what other hidden systems around us are just waiting for you to decode them?